Okay, we are live. So, real gases versus ideal gases. Hello, Sasha. So, remember the bad postulates of kinetic molecular theory. That particles don't interact and that particles don't take up space. But they do interact. That's why we have liquids. The gas particles interact enough that they collapse down into a liquid. All right, and particles do take up space. They don't take up much, but they do take up space. So ideal conditions mean low pressure and high temperature. Low pressure so that the space between the particles is huge compared to the space of the particles themselves, and thus we can neglect the volume of the particles. High temperature so that the particles just don't have time to interact. Real conditions occur if you violate those. So, PV over NT is equal to R. So for an ideal gas, PV over nRT is equal to 1. Because, PV equals nRT. And this is something that they use to track deviations from ideal behavior. So here we have, in Italian for some reason, we have Z, PV over RT, for 1 mole of gas. Okay. Ideally, for 1 mole of gas, Z would be equal to 1. So that is what we have up here. That would be this line. Okay. Z being equal to 1. But we can actually measure pressure and volume and temperature for any given gas, and we can see how this changes. Okay. So each of these lines for a particular gas represents the deviation, sometimes extreme, from the ideal behavior based on pressure. So you see here at low pressures, they all start out fairly close to 1. Each line represents a different temperature as well. They're sort of normalized, so don't worry too much about the numbers. Just we have low temperatures here, and we see incredible deviation from ideal behavior. And then as temperatures increase, they get higher and higher and closer to ideal behavior. You also have the oddity that as pressure increases, you get a more extreme deviation from ideal behavior, and then it goes back up. Don't worry too much about that. That's a complication. But this does demonstrate that ideal behavior really works best at low pressures and high temperatures. So we can also use this to look at different gases. Okay? So here, once again, we have PV over RT, the compression factor, they call it. And this straight line in the middle would be ideal behavior. Z is equal to 1, or PV over RT is equal to 1 for 1 mole of gas. And we can see that different gases have different forms of deviation. So this red line is hydrogen. Okay, it just always has PV over RT greater than 1. And it just keeps on going up and up and up as you increase pressure. Notice that the pressure here, they actually listed in atmospheres, and it's 200, 400, 600. These are very high pressures we're talking about. That's why they went ahead and they did a normalized sort of thing. So these are not atmospheres down here on the bottom. Then we have CO2, where the compression factor, compressibility, excuse me, Z, then goes down and then comes back up over here on the right. Then similarly, methane and nitrogen. So why does carbon dioxide have greater deviation than the others? Why does it, first go way down and then come back up? Well, it's because of, it's because it has greater opportunity to interact. It has greater interaction among its particles. Nitrogen, methane, and hydrogen are all completely nonpolar. Nitrogen and hydrogen, it's just the diatomic elements are the two atoms are completely equal, so there's absolutely no polarity there. Carbon and hydrogen have very similar electronegativities, so those bonds are essentially nonpolar as well. Carbon dioxide, the molecule is nonpolar, but each of those bonds is polar. So there's still a charge distribution inside CO2. Okay, let me bring this up. So when you look at, say, hydrogen, okay, there is absolutely no charge distribution there. These guys are exactly the same. But if you look at CO2, the molecule is nonpolar, but you still have negative partial charges and partial positive charge. So when these guys get close to each other, they can interact in that way. The oxygen atoms will be attracted to the carbon atoms of other molecules. So that's why you get that greater deviation from ideal behavior for carbon dioxide than you do for the others. They all still deviate from ideal behavior because they all still do feel those intermolecular forces, as they're called. And they all do, of course, take up space. But carbon dioxide has stronger interactions, therefore it has greater deviation. So that's something that they could ask you. Which particle, which element, or which substance is going to show greater deviation from ideal behavior? So you're going to be looking for things like that. You're going to be looking for things like polarity. And even if it's nonpolar, does it have polar bonds? Because that will still have an impact. All right. So the way we deal with this, we can still model the behavior of real gases. And we can modify PVNERT to do that. One of the ways we do that is with the van der Waals equation. This is just one attempt people have made. So this right here is how we is a factor that we add to pressure in order to take into account the interactions of the particles with one another. And then over here we have a thing that we add to volume to take into account the fact that particles take up space. These are things that have to be measured, and if you look in your textbook, you'll actually find a table of those things. Well, maybe not your textbook. I haven't looked at this recently, but some textbooks do have some of these factors for some substances. And this is, kind of complicated, but this modification to pressure takes into account not just the attraction of the particles, but it also is modified by how many particles there are and how much space the gas is inside of. Whereas this one is much simpler. It's just the volume of an individual particle multiplied by the number of particles, more or less. They will very likely not ask you to do math with the van der Waals equation, but they could. It's entirely possible. I just doubt it. It's an interesting phenomenon to see. This does make a difference, but you'll notice that the deviations from ideal behavior, you really do have to pump this up to really high pressures before you start to see those deviations. Otherwise, they're not really going to have much of effect. So at low pressures, the pressures we typically work at, behavior is still going to be very close to ideal. Nevertheless, this is, at least conceptually something they could ask you about. I don't think they'll ask you to do the math. They could, but I doubt it. All right, and with that, we are done with Chapter 9, which means that we are done with Chemistry 110. It has been a heck of a ride. I hope to see you again next semester. Well, I might not be teaching Chemistry 111, but hopefully you have done well. Hopefully you will do well on the final exam. Good luck, and I will see you around.